Containers and container orchestrators. In the second lecture, we talked about how applications interact with the kernel and the hardware. By now you know that applications running in Ring 3 do not have direct access to things like the disk. To access those details, they need to execute a system call to the kernel. The kernel will give the applications the details required, for example, a file from the disk. Let's play a hypothetical game. Process A wants to access a file called test.txt. It calls the kernel, the file is opened, and process A is now free to read the contents. When process B comes along and does the same, it will receive the same file. Or does it? In the Linux kernel, the file system root directory, starting with a /, is a virtual construct that can be changed on a per-process basis. It is possible to make process A see a completely different folder structure than process B. This mechanism is called chroot. It is, in fact, so old that it predates Linux by more than a decade and was first present in version 7 of Unix in 1979. This alone isolates the two processes on a file system level, but there are still plenty of opportunities for two processes to interact, for example, on the network, via inter-process communication, sending signals to each other by process ID, etc. In the early 2000s, there were two projects that attempted to implement process isolation in the Linux kernel: OpenVZ and Linux vServer. Running these projects required patching and recompiling the Linux kernel from source. Starting around 2006, several companies including Google, IBM, SGI, Bull and the OpenVZ project itself has put in significant effort into taking OpenVZ apart and piece by piece submitting it to the Linux kernel. The user bean counters from OpenVZ, for example, became C groups and allowed resource allocation to a group of processes. Do you want to know more about history? The history of containerization is surprisingly hard to piece together despite the relative young age of the technology. If you want a bit of a deeper dive, take a look at The Brief History of Containers by Jeff Victor and Kirk Kolschkin. All these isolation techniques together form what's today known as Linux containers. Windows has undergone a similar development in recent years and has virtualized the typical Windows interaction points between processes: job objects, process table, registry, file system, etc. In essence, containers don't exist. They are a collection of technologies that provide process-level isolation for an application. These isolation techniques can, among others, include a separate virtual network card, process separation, so no ability to send signals to other containers, a separate view of the file system, restricted inter-process communication between containers, and user separation or user ID mapping. Do you want to build your own container engine? You can. Take a look at Liz Rice's Containers from Scratch talk. Container images. Docker was not the first technology to create containers using the modern Linux APIs, but it was the one that made containers popular. The edge Docker had over its competitors was the way it dealt with images. Other container solutions at the time, like LXC, tried to emulate virtual machines where a full operating system would be installed and then updated. Docker chose a different route. A Docker file would contain the instructions needed to build a container image containing an application that should be containerized. These instructions would be executed and resulted in a container image. This container image could then be used to launch one or more copies of it. Since the container image contains everything the application needs to run, these images are ideal operating system independent packages. This solves the age-old problem of having to install the correct version of the runtime environment such as PHP, Python, Java, etc., as it is contained within the container image. When a container is run, this container image is the basis for all the data that is contained within. The data is, however, not copied. If the application modifies or creates files, only the difference is stored. This makes containers very lightweight on the storage front as well. Docker went one step further. They introduced a way to share images between machines using a registry, a server that stores container images. The public Docker Hub contains a vast array of images built by the community. These technologies were later all standardized under the Open Container Initiative, creating a company-independent format for containers and the technologies around them. Be careful. Third-party container images should be treated with the same due diligence like installing third-party software on your computer. They can contain malicious code and can cause harm despite the containerization. The container lifecycle. You can, of course, update a running container just like you would a traditional virtual machine. However, that is not the intended or indeed optimal way to use them. The intention of containers is immutable infrastructure. Immutable infrastructure means that a container is never updated. Instead, they are replaced. When a new version of a software needs to be installed, the old container is shut down and a new one is launched from a new image. Immutable infrastructure presents a massive benefit. Instead of having to deal with the downtime when an upgrade is ran, the updated version can be tested before it is launched. However, this concept reaches its limits when it comes to running software that needs to store data in a persistent fashion, for example databases. For this purpose, containers can designate a special folder mounted as volumes. Volumes can be persisted by either mounting them as a folder from the host machine or by mounting a network-based storage system. Orchestration with Swarm, Kubernetes, etc. Docker and other container runtimes do not manage containers across multiple servers by themselves. Docker has received an add-on called Docker Swarm, but nowadays the clear winner of the container wars is Kubernetes. Container orchestrators are responsible for determining which server has free capacity and schedule containers to run on them. When a server fails, these orchestrators are responsible for discovering it and relaunching them on a different server. Furthermore, container orchestrators contain a certain amount of integration with the cloud providers. Docker Swarm has very basic integrations, but Kubernetes, on the other hand, has integrations with just about anything. Depending on the cloud provider, Kubernetes can automatically move block storage mounts to a different server when a container is moved, configure cloud load balancers, and much more. This flexibility comes at a cost. Kubernetes is very complex. A detailed explanation on how to deploy applications on Kubernetes would vastly exceed the bounds of this course. If you're interested in this topic, we recommend taking a look at one of the many certified Kubernetes application developers courses on the internet. Container networking. As mentioned previously, containers regularly have their own virtual network interfaces. This virtual network interface can be connected in a number of ways. If we take a look at Docker's default networking model, the virtual network interface is connected to an internal network bridge. This enables containers to connect to each other. For connections to the internet, a network address translation is performed. More advanced options for container networking create a single virtual network across several hosts and connect the containers to this virtual network. This is an option with Docker Swarm and is always the case with Kubernetes. One question comes to mind though. The cloud is quite dynamic in its nature, so how does a Kubernetes cluster receive incoming connections? After all, each of the nodes may be replaced with a new one with a new IP address at any time. This is where the immense feature set of Kubernetes begins to show itself. Kubernetes includes several controllers that can interact with cloud providers in a variety of ways. One of these interactions can be, for example, the load balancer integrations. The Kubernetes network can be extended to a load balancer, and that load balancer can then send traffic directly over the virtual network used by containers. Further helping with the dynamic nature of the cloud are features like the ability to create internal firewalls. These firewalls can help mitigate possible security vulnerabilities like SSRF. Since these firewalls can be created using the same API as the software deployment, the firewall rules for an application can be versioned in Git, for example. Since everything required to run an application can be stored in a Docker file and a Kubernetes manifest, the application source code can be self-contained. This is, of course, only true if the application is written in such a way that it works well with the cloud. This is described in the next lecture. Kubernetes. We have talked about Kubernetes before, but we are dedicating this section to more details, as it has become quite apparent that Kubernetes is going to be the de facto standard for container orchestration in the future. The history of Kubernetes lies in the Borg orchestrator from Google. The intention is to be able to orchestrate workloads across thousands of machines. Since Kubernetes is highly scalable, its design is difficult to use at small scale. Developer aspect. Developers using Kubernetes are only confronted with a subset of Kubernetes' complexity. A developer can create a Kubernetes manifest file in YAML format that instructs Kubernetes to run a certain set of containers, network them together, provide load balancers, etc. The basic unit of scheduling is called a pod. A pod is a unit consisting of one or more containers that share a network namespace and can potentially also share other resources. Pods can either run continuously or can be scheduled to run to completion for one-off jobs or cron jobs. However, unlike a simple Docker installation, Kubernetes offers a way to manage pods on a higher level. Deployments offer a way to create a resource to manage downtimeless deployments and roll back to a previous version with a simple rollback command if desired. They do this by using a replica set, an automatic resource creating multiple copies of a pod. As you can already see, this highlights what we will discuss in the next lecture. A cloud-native application has to be ready to have multiple parallel copies of itself running. For more difficult workloads, Kubernetes also includes a stateful set. Stateful sets give a developer the ability to guarantee a predictable startup sequence of multiple pods as well as a unique ID for each. This is especially important for replicated databases. Daemon sets, on the other hand, are a special workload type more geared towards Kubernetes administrators, offering the ability to run a workload on every node of the cluster. This is often used to run utility pods such as log collectors, monitoring agents, etc. Since some pods need to store data, Kubernetes offers a flexible way to allocate storage in the cloud with the use of persistent volume claims and persistent volumes. Kubernetes administrator would set up a persistent volume, which a developer then uses using a persistent volume claim. This decouples the developers and the administrators' work nicely. It is worth remembering, though, that a single persistent volume can only be used by a single persistent volume claim. This makes allocation in larger clusters cumbersome. Naturally, Kubernetes has a solution for this problem called provisioners. These provisioners can dynamically create PVs as needed, usually by creating a network block storage volume in the cloud. It is also worth noting that while local storage is supported, it does not provide any resilience against host machine failure, as we discussed in Lecture 2. While Kubernetes will do its best to support local storage and will not reschedule a workload with such an attached storage, it also limits the ability for Kubernetes to react to a node failure and move workloads. In order to facilitate internal and external load balancing, Kubernetes introduces the concept of services to create internal network load balancers for each service. These services use the pod labels to track which pod they should send traffic to. A special type of service is the load balancer, which, given a cloud integration, dynamically creates an external IP address for a specified service. Alternatively, workloads can also make use of the ingress resource that dynamically configures the ingress controller to send HTTP workloads to specified pods. The ingress controller acts as an application load balancer for Kubernetes. To augment these capabilities, the job resource gives developers the ability to use Kubernetes as a queue system and run one-off workloads. To run regular jobs, the cron job resource can also be used. Architecture. The Kubernetes architecture is highly modular and the description given is fairly generic. Individual Kubernetes distributions may differ greatly in their use of tools. At the core of Kubernetes is the API server. This central piece is the endpoint for both clients, for example the Kubernetes CLI called kubectl, other orchestrator components such as the controller manager, cloud controller or scheduler, and also the workload coordinator called kubelet. The scheduler is responsible for deciding which container is supposed to run on which worker node. As the name says, it schedules the workload. The controller manager is a component composed of many small parts that decides what to run. For example, the replica set controller is responsible for creating multiple copies of the same pod. The cloud controller is responsible for the cloud provider integration. This is optional for a static cluster, but required if autoscaling or load balancing integration is required. The kubelet runs on every node and is responsible for talking to the container runtime, for example containerd, to run the containers the scheduler deems necessary. It is worth mentioning that the kubelet must be able to reach the API server on a network level and vice versa. HTTP requests flow in both directions in order to make the Kubernetes cluster work. The kubeproxy service often runs on each Kubernetes node to provide load balancing, but there are replacements for this component. The Container Network Interface, or CNI, is a network component deployed alongside the kubelet and provides the previously described overlay network. There is a wide range of CNI plugins from bare metal routing to Calico. As a final piece of the puzzle, container storage interfaces provide a way to integrate just about any storage provider as a driver for PVs.